Welcome to Physics 550, Solid-State Physics. This is Module 7, covering transport phenomena and magnetism. Module 7 is divided into two parts: transport, which explores the movement of charges and heat through the solid state, and magnetism, which examines how atomic spins align and interact. We begin with the Drude model. It treats electrons as a classical gas, scattering off stationary ion cores. Its core assumptions are independent particles, stationary cores, and classical mechanics. The Drude conductivity formula, sigma equals Ne squared tau over m, defines conductivity using four key parameters: carrier density, charge, relaxation time, and mass. The Boltzmann equation shifts perspective from a single particle to a collective probability fluid, explaining how statistical distributions shift. This view is crucial for explaining the exact temperature dependencies of conductivity. The Hall effect is a key transport phenomenon. The Lorentz force deflects moving charges perpendicular to both the current and the external magnetic field, generating a measurable Hall voltage. The Hall coefficient formula, R sub h equals -1 over Ne, allows us to determine the dominant charge carriers. A negative R sub h indicates electrons, while a positive R sub h indicates holes. The Wiedemann-Franz Law relates thermal and electrical transport. The ratio of thermal conductivity to the product of electrical conductivity and absolute temperature equals the Lorentz number, a constant for metals. This matrix summarizes the three transport models. Drude provides basic conductivity, Boltzmann explains temperature dependencies, and the Hall effect determines the sign and density of charge carriers. Moving to magnetism, we shift from electron fluids to stationary, bound magnetic moments. The origins of magnetism lie in two sources: the electron's orbital moment and its intrinsic spin. Diamagnetism, or Langevin diamagnetism, is a universal resistance based on Lenz's law. An applied field induces a small, opposing magnetic moment, resulting in a negative and very weak susceptibility. Paramagnetism involves permanent atomic dipoles attempting to align with an applied field, constantly disrupted by thermal energy. Curie's law shows susceptibility is weak, positive, and decreases as temperature increases. Ferromagnetism involves spontaneous magnetization due to the quantum mechanical exchange interaction. This strong linkage overpowers thermal disruption below the critical Curie temperature, T sub C. Magnetic domains form to minimize magnetostatic energy, fracturing the crystal into distinct regions with zero net magnetization. Hysteresis occurs when domains aligned with an applied field grow by shifting block walls. Antiferromagnetism is characterized by hidden order. Below the Néel temperature, T sub n, neighboring spins order in opposite directions, resulting in exactly zero macroscopic net magnetization. Spin waves, or magnons, are quantized ripples in the magnetic alignment, similar to how phonons are quantized vibrations of the atomic lattice. Thermal energy excites these waves, slightly reducing the total magnetization. This synthesis matrix summarizes the four main states of magnetic ordering: diamagnetism, paramagnetism, ferromagnetism, and antiferromagnetism, based on their spin alignment, susceptibility, and temperature dependence. A key real-world application is the Hall effect sensor. Automotive ABS sensors use the Hall effect, where a steel gear tooth disrupts a magnetic field, generating a readable digital pulse for speed sensing. Another vital application is magnetic data storage. The read-write head exploits magnetic hysteresis to flip ferromagnetic domains up or down, permanently locking in binary data represented by the ones and zeros. Solid-state properties emerge from the transition between the kinetic motion of charges and the static ordering of spins. Remember to synthesize concepts rather than just memorizing derivations before moving on to Module 8, Superconductivity.